My name is Kevin Backhouse and I'm a member of GitHub Security Lab. This presentation is about dbus. dbus is a messaging system that's widely used on Linux for inter-process communication, or IPC. And in this presentation, I'm going to focus on how it's used by many of the system services that are running in the background. I'm going to try to give you an overview of dbus's architecture with a particular focus on its security features. And I'll also go into a bit more detail on Polkit, which is the service that's responsible for checking whether a user is authorized to do something. I'm going to show you a few source code examples of what it looks like to program a dbus service, and I'll talk about some of the most common bug classes that I've seen. Finally, I'll show you a couple of demos of local privilege escalation vulnerabilities that I've found in the past year. Usually, privilege escalation vulnerabilities on Linux are caused by bugs in either the kernel or a setuid binary like sudo, but these vulnerabilities were caused by bugs in dbus services. So let's do a quick demo of dbus. Now, just to be clear, this first demo is not a demo of a vulnerability. I just want to show you what it looks like when things are working normally. So I've got a VM running here, running Ubuntu 20.04. And this is the system settings dialog box. And many of the things that you do in this system settings dialog box are going to trigger dbus events. So for example, if I change the icon here, that was a dbus message that got sent in the background. But dbus is not just a graphical thing. It's mostly happening in the background. And so you can also send dbus messages from the command line. So I've got a little cheat sheet here that I'm going to use. And I'm just going to use the command line now to change the icon again. So if I go back to the system settings, you can see that the icon has changed. Now, few things that I just want to point out in this command here. There's always a destination on a dbus message. There's always a path as well. And the path, so some dbus services have a whole tree of different objects, and so the path tells you which of those objects you want to interact with. And here we're interacting with user 1001, which is my user ID. Then there's a method name, so set icon file in this case, and sometimes there will be a message body. In this case, the message body is a string with the path of the file. So this is an architecture diagram of the dbus ecosystem. At the center, there's this process called dbus-daemon, which is responsible for routing dbus messages to the correct recipient. dbus-daemon also has an important role in the security of the whole system, which I'll talk about in more detail later. In this diagram, I've also included examples of some important system services that participate in this ecosystem. So, for example, you've got systemd there, the accountsservice daemon, Polkit, etc. And Linux itself forms the base layer of it all. The two most important things that Linux brings to this party are, firstly, of course, the usual process and user account separation stuff, so that these system services are all properly isolated from each other. And secondly, Unix domain sockets, which are used for secure communication. A Unix domain socket is similar to a TCP socket, but because it's handled by the kernel, you don't need to worry about encrypting the messages, for example. And it can do some things that TCP sockets can't do. Like, for example, you can send a file descriptor over a Unix domain socket, and you can also use it to check the credentials of the process on the other end. So I think this architecture is one of the things that has led to this joke that Linux is what the systemd operating system used to be called. This is one version of that joke that I saw on Twitter recently. This particular version of the joke is quite good because it's riffing on the old GNU Linux thing. Just as an aside, I don't personally quite understand why some people are so upset about systemd. It seems fine to me, and from what I've seen of the source code, it looks quite well written. But I do think that there might be some truth to this joke. So earlier this year, I started reading this book. I skipped the operating systems class when I was in college, so I decided it was time to catch up. I have to admit, I've not made much progress yet. But this was around the same time that I was learning about dbus. And I was really struck by the similarity between the dbus ecosystem and this description of the Minix microkernel operating system. So it says here, unlike Unix, whose kernel is a monolithic program not split up into modules, Minix 3 itself is a collection of processes that communicate with each other and also with user processes using a single inter-process communication primitive, message passing. Now, I don't think anyone's going to accuse Linux of being a microkernel operating system, but maybe parts of the design are moving in that direction. Okay, let's have a look at a few examples of dbus messages so that you understand the basic format. Now, bear in mind that dbus messages are a binary format, so what you're looking at here is a pretty printed rendering of it. So these two messages are quite similar, but the one on the left keeps repeating org.freedesktop.account. So I included the one on the right to show you that it isn't always like that. Now, these messages are both method calls. The other message types are replies, errors, and signals. Signals are kind of like broadcast messages that you can subscribe to. The message serial number is important for replies. So sometimes you might have to wait a while before you get a reply to a method call that you sent. So the serial number is useful for tracking. Now, there's a few different header fields, some of which are optional, depending on what kind of message you're sending. And we saw examples of several of these fields when I used dbus-send to send that message on the command line earlier. Now, there's two fields that are kind of special. The first is Unix FDs, which allows you to attach file descriptors to the message. So that can be used, for example, to share a file with a system service in a reliable way that isn't vulnerable to something like a TOC2 attack. The second is the sender field, which is added by the dbus-daemon. So that's really valuable for security because the sender field can't be spoofed. It allows system services to reliably check things like what the user ID is of the sender that they just received a message from. And finally, messages can optionally include a body with a list of extra arguments. And the type of the data in the body is determined by the signature header field. Now, in this slide, I'm showing you an example of a method call on the left and its reply on the right. This particular message is actually quite an important one. It's the hello message, which is always the first message that you have to send when you first connect to the dbus-daemon. And the reply that you get back from the dbus-daemon tells you what your unique bus name is. So in this example, it's 1.3591. One of the things I want to emphasize here is the distinction between unique bus names and well-known names. So a well-known name is something like org.freedesktop.accounts, and typically only root processors are allowed to claim those well-known names. That's a security feature to prevent an unprivileged process from impersonating a system service and using that to intercept important messages. So just to summarize, what are the main security features of dbus? It gives you secure inter-process communication. The ownership rules on well-known names ensure that system services can't be impersonated. And unique bus names allow you to reliably check the credentials of your counterparty. So sometimes you see code where they've used the PID for that instead, and that's a bug because PIDs get recycled frequently. So unique bus names are a much better solution because they never get recycled. The final one is a feature that I didn't mention yet. You can also set restrictions on which methods are allowed to be called. For example, you might have some methods that are only allowed to be called by a root process. I think the thing that I like the least about, or that I dislike about dbus is the proliferation of config files. I can never remember where they all are, and I have no doubt that I'm going to end up using these slides as a reference next time I'm trying to find one of them. So these files that I've listed here are the config files for the account service. And the directories that these files are in contain many other config files for all the other system services. And in fact, this isn't even the full list, because there are also other config files relating to Polkit. Okay, so I just want to quickly show you what's in two of these config files. The first one is the systemd service file for the account service. The important thing here is that many of these services can be started on demand, so they don't need to be running all the time. So if, for example, you send a message to the org.freedesktop.accounts and the account service daemon isn't running yet, then it gets started up automatically and then it replies to your message. And so you never needed to know that it actually needed to be started up for your benefit. This second config file defines the security policy. So first of all, at the top here is where it says that only a root process is allowed to claim this well-known name, which is what prevents an unprivileged process from impersonating the account service. And down here is where it defines the rules for sending messages to the account service. Now, these aren't quite so interesting, because I was going to show you a second one here. So this is the config file for systemd login-d. And what you see here is that login-d has this rule which says deny by default. So that's something that you can do if your service is highly security critical, like login-d is. Okay, it's time for another demo. So, like last time, this is not a vulnerability demo yet. I just want to show you how Polkit works. So, if I go to the settings dialog box here, if I do something like clicking this unlock button, then you see this dialog box popping up. This dialog box is known as an authentication agent. And so a root user or an admin user, like the other account on this machine, Kevin, needs to enter their password here in order to authorize that. Again, it is not just a graphical thing, though. So if, for example, I were to try to create a user account with this dbus message on the command line, then you get that same dialog box again. Now, it doesn't even need to be a graphical dialog box. An authentication agent could even be text-based. So if, for example, I SSH in so that I'm on a text mode session, and then there's another command which also requires Polkit authorization called pkexec, and that program actually starts its own text mode authentication agent when it's in a text-based session. And so you can see here that it's asking for the password on the command line. Okay, so in this diagram, I'm going to try to explain the architecture of Polkit. Now, the first thing to note is that everything above the dotted line is an unprivileged process. So the thing that's quite interesting there is that the authentication agent is not a privileged process. That dialog box is basically just a way of getting your password to Polkit. So the first thing that happens is that the authentication agent registers with Polkit, and that's something that can happen as soon as you log in, so that that authentication agent is already there, ready to go when you need it. Now, suppose you do something like clicking that unlock button or trying to create a new user account. Then what happens there is that a dbus message gets sent to one of the system services, and in this case, that's the account service. And an important thing to notice there is that the dbus-daemon has added the unique bus name for the message, for the sender of the message. So now the account service needs to check whether the sender is allowed to create a new user. So it sends a check authorization message to Polkit, and it includes the unique bus name in the message so that there can't be any ambiguity about where this request came from. Now, sometimes Polkit is able to approve or deny the request instantly. For For example, if the request came from a process that's running as root, then it will immediately send back an access granted message. But most of the time, it's going to need to pop that dialog box, and it does that by sending a message to the authentication agent. And it attaches a cookie to that message, which the authentication agent is going to send back later. Now, remember that the authentication agent is not running as a privileged process. So how is Polkit going to trust that the password was checked properly when it gets that cookie back from the agent? The way that that's done is that there's this set UID program called Polkit Agent Helper 1 that does the actual checking of the password. So that thing runs as root, and Polkit is only going to trust the response if it receives it from a root-owned process. So the final step is that now that the password has been checked, Polkit sends back an OK reply, and accountsservice will now go ahead and create that new user account. Now, one final thing that I want to point out here is that it can take quite a long time for accountsservice to get that reply back from Polkit, because you have to wait for the user to type their password into that dialog box. And meanwhile, the account service might have to deal with other requests that have come from other processes. So one of the things that all dbus services and the libraries that they use have to be able to deal with is asynchronous communication. And we'll see some of that later. Okay, so let's have a look at Polkit's config files. These are, again, very important because a mistake in one of these files could completely undermine the security of the whole system. Now, the first of these directories is the standard location, but the second is a little bit obscure. In fact, it took me quite a while to discover this second location, and it's relevant to one of the vulnerabilities that I'm going to show you later. Okay, this is an excerpt of the config file for the account service. And you can see that it defines these action IDs. And then it defines who is permitted to do those actions. So changing your own user data, that's just allowed with no further questions asked. It says yes, yes, yes there for the permissions. But user administration, so that's things like creating or deleting accounts, for that you need to have admin privileges. So down there it says admin. Now, this is one of those config files from that obscure second directory. And this config file is granting special privileges to a user named GNOME initial setup. And so you can see here that one of the things that it's giving GNOME initial setup permission to do is anything relating to the account service. So GNOME initial setup is effectively root. So it turns out that the reason why this exists is that when you first install GNOME on a new computer, you're presented with a series of dialog boxes that help you to create an account on that computer. And those dialog boxes are running as the GNOME initial setup user. And you're going to see those dialog boxes in one of my vulnerability demos later. Now, I want to show you some examples of what it looks like to program a dbus service. Typically, if you're implementing a dbus service, then you're going to use a dbus library to do that. And there are four main ones that I'm aware of. I'm only going to show you examples from two of them, though, the Python one and the systemd one. So what do these libraries do? Well, obviously, they need to be able to parse and serialize dbus messages. But they also take care of listening on that Unix domain socket and dispatching the incoming message to the correct place. And they usually have some way of helping you with the asynchronous communication problem that I mentioned a few slides back. Okay, so this example is from the Python 3 apt-daemon application, which is a service that you can use to install software. Let me just make that a little bit bigger. So this is the install packages method. And you can see here that it's got this decorator on it, which declares the dbus interface to this method. Now, I'm not an expert Python programmer, and so I've got to admit that I don't fully understand all of the magic that's happening here with this decorator. But you notice that it has deferred in its name. So this allows you to pause the code while you're waiting for one of those asynchronous calls to finish. And you see that here. This is the code that aptd uses to call out to Polkit. I just made that bigger there. So this is where it's calling Polkit. And you can see that it's registering this callback function here. And what happens there is that this code will get paused until the reply comes in, and then that callback will get called once the reply has arrived, and that's when the deferred code starts running again. Okay, so the second example is from systemd logind, and I'm just going to make that a little bit bigger again. So this is C code, so it's a bit lower level. And so, for example, you can see here that they're having to use this library function to read the contents of the message, whereas in the Python case, that was handled by that magic decorator. Now, the way that systemd handles the asynchronous communication with Polkit is, I think, quite clever. C doesn't have any built-in support for closures, so doing something like that deferred stuff that we just saw in Python would be really quite awkward. So what systemd does instead is basically just replay the whole message again. So the first time that you call this verify async function, it returns 0, which means I'll call you again when I receive the reply. And on the second run through, it will return either a positive number or a negative number, depending on whether the request was authorized. Okay, so let's talk about common bug categories that can happen in these dbus services. Now, many of these services are written in C, so you'd think that many of them would have memory corruption vulnerabilities. But actually, I've had zero success in finding any of those kinds of vulnerabilities. Obviously, doesn't mean that they're not there. It's just that I haven't been able to find them myself. But I do think that maybe because most of these applications are using these dbus libraries to do the lower level message parsing stuff, that maybe that's why I've not found many vulnerabilities, because those libraries have been quite well tested. What I have seen a lot of is privilege dropping mistakes. So quite often, a user will send one of these services a path to a file, like, for example, when we changed the user's icon in that demo earlier. So if the service is running as root, then it needs to be careful not to use its root privileges to read that file. Otherwise, that could potentially lead to an information disclosure vulnerability. So instead, the service will often change its UID so that it can only read the files that you can read. But if it does that incorrectly, then that can lead to a denial of service vulnerability. And so I'm going to show you examples of both of those problems in a second. File system time of check, time of use vulnerabilities are another similar kind of bug. But the two most serious bugs that I've found have both been caused by bad error handling. In both cases, that led to local privilege escalation, and those are the demos that I'm going to show you in a minute. Okay, so this is an example of a file existence disclosure bug. Let me just make that a bit bigger. So the bug here is that debconf socket is a path that was sent by the user, and aptd is using its root privileges to check whether that file exists. And the problem is that you can tell from the error message that, whether or not that file exists or not. Now, that's not a very serious vulnerability, but sometimes bugs like this can be quite useful as part of an exploit chain. Now, this is an example of a denial of service vulnerability in the account service caused by bad privilege dropping. I'll make that bigger again. So you can see here that it's temporarily dropping privileges to read a file, and then it regains them again afterwards. But there's two problems here. The first is that you could supply a malicious file that makes this loop run for a really long time. And the second bug, which you can't see in this code snippet is that they dropped the real user ID as well as the effective user ID, which meant that the user could send signals to the service. And so in the demo later, I'm going to use that to send the kill signal to the account service and make it crash. Now, this is the first of one of those more serious error handling bugs. It's in GDM3, which is part of the GNOME graphical environment. Let me make that a bit bigger. So what's happening here is that GDM3 is asking the account service how many user accounts there are on the system. And the reason it's doing that is because if there's 0 user accounts, then that means that this is a first-time installation. And it's going to trigger GNOME initial setup, which is going to allow you to create a new account with admin privileges. So the bug here is that if the dbus call fails, then it doesn't set the value of have existing user accounts. And unfortunately, the default value of that field was false. So in the demo, I'm going to make that call fail by crashing the account service, and that's going to lead to a bypass here. Okay, it's time for the first vulnerability demo. Now, just to be clear, these vulnerabilities are already fixed, but in this VM, I've installed the older versions of the software that had the vulnerabilities for the purposes of this demo. Now, in this demo, there's going to be a delay in a minute while it does some stuff. And so what I'm going to do is I'm just going to type a bunch of commands quickly, and then I'll explain what happened during that pause. So I am going to create a symlink in my home directory. And then I'm going to go to the system services or the settings dialog box, and I'm going to change my language. And that's going to trigger that loop that we saw earlier on. And then I'm going to remove that file again, and I'm going to cause the account service to crash, and I need to quickly log out after issuing this command. Okay, so hopefully that should trigger the bug. So let me just explain what was going on there. So I created a symlink from a file called .pam environment in my home directory to dev0, and that triggered that loop that we saw earlier. Then I changed the language in the system settings, and that actually was the dbus message that triggered the account service to run that loop. And then I removed the file so that I can log in again afterwards. And so then the next thing was that I needed to trigger the error handling code in GDM3, and that was triggered by logging out. And just before I did that, I used that no-hop command to set a little timer so that the kill signal would be sent to account service shortly after I'd logged out. So that created the timing so that when GDM3 sends its message, the account service is still alive, but then it dies shortly after that. And so that then triggered the bug. It thinks that we're in an initial setup now, and so now it's running that GNOME initial setup code, which is going to allow me to create a new user account. So just quickly click through these dialog boxes and enter a new username. And so that has now created a new user account called Indiana. And we'll see in just a second that Indiana is an admin user. So if I do ID here, you can see that Indiana is a member of the sudo group. Okay, I'm going to just log back out and log back in as Junior for the next demo. Okay, so the second vulnerability was also caused by bad error handling, but this vulnerability is in Polkit itself. So this code that you see here is used when Polkit is checking whether or not you're already authorized to perform an action. So what it does is it asks the dbus-daemon for your credentials. And if, for example, the dbus-daemon says this user is root, then it's going to immediately approve the request. Okay, so let's zoom in here. So this bug is very similar to the last one. So it sends a message to the dbus-daemon, and when it gets a reply, this callback function is called. And what that callback function does is it sets the fields of the struct called data. Now, normally it would set the retrieved UID and retrieved PID fields, but when an error occurs, it sets the caught error field instead. But when that happens, it still ends up returning true. And because the UID and PID fields were never set, they end up remaining 0. And so it actually then looks like the caller was a root process. So really the only question is, how do we trigger an error here so that that code path will get taken? And the answer is that you can do that by disconnecting from the dbus-daemon while Polkit is halfway through processing this code. So let's demo that now. So I'm going to run the same command that I did before, which is trying to create a user account called Boris. Now that dialog box is going to be kind of annoying, so it's going to be better if I run it from a text mode session so that we don't get the dialog box. So if I run that there, then it gets instantly denied. And so what we're going to do now is we're just going to add this little bit on the end, which kills it after it's hopefully approximately halfway. It's a little bit non-deterministic because getting the timing right isn't always timing isn't always the same. And so, see, yeah, that didn't work the first time. So usually we have to run it a few times to get it to work. So I'm just going to do that and then see if, yep, Boris has been created now. And you can see that Boris is a pseudo user. But Boris doesn't have a password yet. So I'm going to have to run this exploit a second time with a different dbus message in order to give Boris a password. So I'm going to use this OpenSSL command to convert the password into a hash. And then I'm going to paste that hash into this command here. So put that in there. And then I'm just going to run that a few times again. Hopefully that will have worked. A few more for luck. And let's see if we can log into the Boris account. And the password is I am invincible. And that worked. And so you can see Boris is a pseudo user, and that means that you can become root like this. Okay, that was the demo. So that's about it. To conclude, I think that dbus is quite a well-designed IPC system, but some parts of it are a bit complex, and complexity can cause accidents. The most common types of bugs that I've encountered have been privilege dropping mistakes and bad error handling. The privilege dropping mistakes have generally been relatively minor problems, but the two error handling bugs that I've found have led to quite serious privilege escalation vulnerabilities. Thanks for watching.